Hello once again. Thanks for joining us. My name is Andrew Dunkley, the host of this here podcast called Space Nuts. Great to have your company. I hope you're well. Coming up on this edition, an unusual planet formation discovered. What's that mean? Well, this is a planet that's being born a very different way, it appears, and a spacecraft that's going to be built of Lego.
Ish,
could be, and much, much more. A couple of questions. Oh, look, a black hole question. How different? And we're going to talk about temperature and spacecraft that are exposed to the sun and how they protect them. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
It's so good to have your company. Thanks for joining us on episode 299. We are one short of 300, but apparently we're all away next week, so we're not going to do it. And joining me as always to talk astronomy and space science is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. How are you doing today?
I am well. What about you? How are you recovering from your exposure to the dreaded COVID-19?
Yeah, it's a slow process. I'm doing okay, feeling fine generally.
Yeah.
You're just aware that something's not quite right. A little bit of congestion, perhaps, and things of that sort. No, I'm okay.
Everyone I've spoken to who's had it has reported some kind of different after effect. I've spoken to people who've just had a little bit of, baby brain, if I can call it that.
Yeah.
They're just they can't stay focused. Energy, loss of energy is a big one. Persistent cough, just a little bit of heavy breathing type of stuff. None of that, nasty stuff on the phone, but just a little bit of trouble with normal breathing, that kind of thing. Everyone's got a different story, which I find fascinating, but disturbing all at the same time. Okay, Fred, I'm glad you're on the mend. That's the good news.
I think so, yes.
Now, for those who are wondering what's going to happen with episode 300 next week, we have a plan, which I will tell you later, because we want to get to our first story. I'll just put that on the bottom of my run sheet so I don't forget. But an unusual planet formation has been discovered. Was this the one I heard about that was through Hubble?
Yes, it's a Hubble discovery,
Okay.
as these things often are. And it's one of these stories that doesn't exactly upend what we know already, but it certainly, casts a new light on the way we think things work in space. So you and I have talked many times before, Andrew, about planet formation, and the standard method is something that's usually called the core accretion method. So what you get is bits and pieces sticking together, small objects, basically bits of dust to start with, that gradually stick together. That's what the accretion means. It's things sticking together and forming eventually solid lumps, and eventually those solid lumps come together to form what are called planetesimals, which might be a couple of 100 kilometers across. And then they too stick together to form protoplanets, which might be, the size of Mars or the size of the moon or something like that, which eventually collapse to form the core of planets. And I think in this specific case, Andrew, we're talking about gas giants, the likes of Jupiter, the big planets, how they're formed. So the core accretion method is the standard way that we think planets of this kind were formed. However, some new observations, which have come from direct imaging taken with the Hubble Space Telescope, long may it continue, it's still doing fabulous work, that seems to be, and it's a protoplanet that's forming through a different method, which is being called disk instability. So core accretion is the normal one that we think we observe. Disk instability is what the researchers themselves describe as an intense and violent process because core accretion is a fairly gentle process. There are collisions involved. Things smash into each other and, forms debris again, and then the debris re-sticks together. But generally speaking, the coming together of bits and pieces is relatively slow. It's as these objects come together under their own mutual gravity, and eventually, there's so many of them that they heat up, and that forms a kind of melting that allows the things to stick together. So it's not a violent process, whereas disk instability seems to be. So, what are the observations about? Well, it's a planet around a star called AB Aurigae, which is in the constellation of Auriga the Charioteer, which is a Northern Hemisphere constellation. It's right above Orion in the Northern Hemisphere. Its brightest star is Capella, which is actually a Sun-like star. But AB Aurigae is actually a variable star, which is why it's got that slightly peculiar name. And we can see a disk of protoplanetary material. So one of these protoplanetary disks, which we've talked about many times before, usually because of observations from the ALMA Atacama Large Millimeter Array. But as I said, these are Hubble observations. They've used a Space Telescope imaging spectrograph and their near-infrared camera and multi-object spectrograph. So these are two different instruments on Hubble that have been used. In fact, in connection too with instruments on the Subaru telescope, that's the 8.2 meter telescope operated by Japan at Mauna Kea in Hawaii. So this is the coming together of some of the world's great facilities, the Hubble and Subaru. And what's been observed is this disk. Now, we're very fortunate in this case because this protoplanetary disk is actually face on to our line of sight. So we can see it sort of almost in plan, Andrew, kind of mapped out for anybody to see. And what has been detected is structure in the protoplanetary disk, which includes one very bright part that is being interpreted because of the observations, the spectroscopic observations, as this process of this violent and the expression, an intense and violent process, a planet forming by disk instability. It appears as a bright spot in the images that we've seen. There is a lot of emphasis on exactly what is being seen here, because if you can observe over a long period, and they have done, which is actually one of the reasons why the Hubble telescope's been used for this. They've observed this thing with the Hubble over a period of 13 years. That allows you to see the orbital motion of this thing. So you can actually see this planet moving in its orbit over only a small distance because it's a long way from its parent star. It's about 3 times as far away as Neptune is from the Sun. So it's way out in the depths of its solar system. But the motion has nevertheless been detected, and this process that's going on has also been detected spectroscopically. So it's an exciting result.
Yeah, it's also something we've caught in the early stages of solar system formation. I mean, you compare the age of our solar system to what's been discovered, it's quite young, 2 million years old, they reckon.
Yeah, compared with the 4.57 billion years for our solar system. So we are talking about two very different, epochs or periods in planet formation. But no,
I suppose people would find it surprising that planet formation is still sort of in early phases in some parts of the universe. But I guess if the universe continues to expand, there are always going to be, well, not always because it's all going to end one day, but there's going to be these processes happening at different stages.
Yes, that's the great thing about astronomy. We look out into space and we can see all these phenomena happening at different phases. It's why we know so much about the way stars evolve, Andrew, because we can observe stars at different phases in their lifetimes, from the youngest to the oldest, and indeed even beyond the grave, we can see them because we can see black holes.
Yeah.
So it's a really It's one of the one of the attributes of astronomy that you can look at many different objects, and we can see all these different phenomena. And planetary formation, of course, is one of the hot topics in astronomy at the moment. So it's very much in the forefront of the research field. Looking at the way planets form, and this is a very nice story that comes directly into that into that arena.
Now, you said because of the angle, we can actually see it sort of side on. Someone's going to ask why that's possible, given everything sort of spreads out on a plane in the universe, or does it?
Well, not really, no. So things, we see things at different angles. Galaxies come at different angles, which is why some of those we see face on, some we see edge on, some we see in between. It's a mishmash, and the same. So this is an object in our galaxy. And we're observing it just at exactly the right angle to see the disk face on, and that will be the case for a few million years yet. So we're not going to lose that that angle that it presents to us, not for a while.
So okay, we're saying this one's 2 million years old. When will it be at a point where it's, I don't know, a normal solar system?
That's a great question. And it's, once again, that's the subject of debate. How long does planet formation take? And the current thinking is that it's a pretty rapid process, that, the planets, if you look at our own solar system, for example, as I said, 4.57 billion years old. But we think that the planets, as we know them today, would have been formed within the first 100 or 200 million years of that time. That it's a really early, a really rapid process at the start of a solar system's life. Gets all the nitty gritty ironed out. There would have been. We know that there was a phase, probably 500 million years later, maybe 600 million years later, where everything was charging around and everything was colliding into everything else. A period that we call the late heavy bombardment, and that late heavy bombardment also stirred things up a lot. What caused most of the craters on the moon, for example. But even then, it was relatively small chunks, leftover bits of debris that were charging around, not big protoplanets themselves.
Fascinating. I've just done a quick calculation.
Oh, good.
And,
I wondered what you were up to.
If you're right, well, I had to work it out. Probably wrong. My mathematics sucks. But if you're right about it taking about 200 million years for the solar system to form, we will be able to report on it on episode 10 billion of Space Nuts.
Okay. That's something to look forward to. Yes.
Yeah. Maybe. All right.
Are you sure?
We'll leave it there.
Are you sure it's not episode minus 10 billion that we would be reporting on it? Because we'd have a grandstand seat in front of all the action for that.
Yes, we would. Could be. That's a good thought, and also very confusing. This is Space Nuts with Andrew Dunkley and Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, Fred, let's move on to our next story. And this one seems to have a lot of elements to it. But they're looking at building this massive space station. You suggested out of Lego, but not real Lego,
No,
probably. But are they also looking at artificial gravity in this experiment?
That's right. So that's what this is all about. It's how you can, transfer the idea of a spinning space station into reality. To provide simulated gravity for its occupants. And of course, this all goes back decades. I'm sure many of our listeners will remember the rotating space station in 2001: A Space Odyssey, which was right on the money as to how you might do this. And it's an idea that's been studied in great detail. In fact, a few years ago, I had the pleasure of talking to a gentleman. It's actually Linda Spilker's husband. You remember Linda Spilker, who was the mission scientist project scientist for Cassini?
Yes.
Her husband actually runs a company that looks at exactly this sort of phenomenon, the idea of providing artificial gravity. And I had some really interesting talks with him about the limits on how well this would work. And it turns out that what you've got is some sort of disk, and the humans are around the edge of it, or other objects that you want to put into artificial gravity. But it turns out that if you spin it at much more than about 3 revs per minute, then everybody gets sick, because you're just like in a washing machine. And so what you have to do is spin it at a slow speed, and the slow speed then dictates that you're talking about something big. You're not talking about a disk that's 20 feet across. You're talking about something a kilometer across, so that you get the proper effect of gravity on scales that don't make you sick, basically. And so what this story is about is it's really just a progress report, I guess, on projects that are being looked at through the NASA Institute for Advanced Concept, NIAC, and they basically issue grants to universities and things like that. And 2 of these grants have gone to teams at Carnegie Mellon University and the University of Washington for basically clever ideas about how you can build a kilometer scale space station, which will rotate and have artificial gravity.
Yeah.
Now, kilometer long structures are not things that you can carry up easily on spacecraft unless you're very clever about the kind of technologies that you would use. And that's really what this is all about. It's the structures. And you're quite right. It's not Lego like things. It's basically structures that fold up to be very, very compact. But
more like a Meccano.
Yeah, that sort of thing. That's right. If you, I remember making Meccano bits and pieces that.
Me too. I love that stuff.
Yeah, it was great. So that there is a technical term for the kind of thing that we're talking about, which is a high expansion ratio deployable structure, or a HERDS, HERDS, which is quite a nice, acronym for this sort of thing. So what do we mean?
I hadn't heard of that.
No, I hadn't either. I hadn't heard of it. Thank you, Andrew. That's a very nice pun there that went right over my head.
It's not a very nice
15 seconds.
Terrible.
There must be another one in there. Look,
Don't start.
Herds of ideas come this way.
Oh, dear.
But the name tells you what's
moving right along.
Yes. High expansion ratio deployable structure. So high expansion ratio means it's the ratio between what it's like when it's folded up and when it's not. And it's a very high ratio, and probably with numbers in the hundreds. So this thing gets hundreds of times bigger when you press the button and it is deployed. That's the deployable structure bit. And so there's actually a really nice piece which I think was originally on Universe Today. I saw it on SciTech Daily, which has got some videos of some of these structures being used or being deployed. Where you basically you press a button or release something and it springs into action. It's a bit like I guess a nice way to think of it is when you press the button on an umbrella that opens up on its own. You click the button and suddenly it's gone from a long stick into something that's going to keep the rain off you. And that's very appropriate as I speak, because it's pouring down again here in Sydney.
Oh, gosh.
Once again, the gutters are overflowing. Anyway, never mind all that. If we were outside, it would be very nice to have an umbrella in this weather. And that's basically, I guess, a HERDS, an example of a HERDS, high expansion ratio deployable structure. Oops, sorry. Yeah. So, and I think this is really promising. I love the idea of creating large space stations. I've kind of rambled on about this before, because, if you want to colonize space, the way to do it is by building these large artificial structures. You provide your own gravity, and you essentially allow the engineering to dictate where you're going, rather than the fact that you've got a nice Earth-like planet next door, similar to Earth next door, for example, Mars. Which is why I don't think we should be colonizing Mars. I think we should be building herds in space. There you go.
Yes, fair enough. I did see an interesting science fiction solution to the artificial gravity problem in the TV series The Expanse, which I thoroughly enjoyed.
Okay.
What a great show.
Yep.
The special effects were amazing, but they didn't have artificial gravity on most of their spacecraft. But they did have electromagnetic boots.
Okay.
and the floors were all made of metal. So you just turned the boots on and you could walk around.
Yeah. I think,
I think the problem with that is if you're in space long enough, the muscle wastage would eventually make it more and more difficult for you to walk with magnetic boots. That's the only problem I can see with it.
So when we were in COVID lockdown last week, we explored the extremes of what's available on TV, on the web. And I picked out because I wanted to pick out one of my favorites. And so we wound up with Wallace and Gromit, Andrew. And I don't know whether you remember, but one of the episodes of Wallace and Gromit is called The Wrong Trousers. And it's got exactly what you're talking about there, except they weren't magnetic. They were vacuum operated, a bit like fly's feet, I guess. Suckers on the bottom of your trousers, allowing you to walk along ceilings and things of that sort.
There's such clever stuff, that. Well, the latest science fiction series that I've attached myself to, because I used to play the game with the boys when they were young, is Halo.
Yeah, well, Halo's the classic example of a rotating structure.
Yes, and the critics have been pretty nasty with the TV series of Halo.
Yeah, I didn't know there was.
And a lot of the purists are saying, but I'm just taking it on face value. I'm loving it. I'm really loving it. And the special effects are magnificent.
That sounds great.
So, but I can relate to the characters because they're all straight out of the game.
Yes.
There's a couple in there. The only thing that disappointed me is when the very first edition of the Halo game, when it came out, started with a movie role introducing us to the Master Chief, but also the spaceship, the battle cruiser he was on, called the Pillar of Autumn. I loved the names of things in it. The Pillar of Autumn. It was a great name. But they didn't start it that way. They started on this planet we'd never heard of with these characters that we never heard of. So maybe that put people off initially. And guess what they were mining on this planet? You'll never get it.
Wouldn't be cheese, would it?
No, deuterium.
Deuterium.
Yeah. I don't know what they wanted to use it for. They didn't.
Yeah.
They never explained that, but it was a highly sought after commodity. Yeah, possibly. Yeah. Anyway, and I'm also interested to see that China is very keen on this experiment. They're obviously keen to get artificial gravity solved as well. I guess anybody who's going into space would like to solve it.
Yeah, that's right.
Okay. We'll leave it there for the moment, but if you want to chase that story up, it's on scitechdaily.com. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Space Nuts. You'll be listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.